Chapter 6, Section 5 is about conditions for special parallelograms. So by the end of this lesson, you should be able to prove that a given quadrilateral is a rectangle, a rhombus, or a square. And we have certain conditions that each of them have to meet. So when we have a parallelogram with some properties, we can use the theorems that we know to determine if it's a rectangle. So the first one is, if one angle of a parallelogram is a right angle, then the parallelogram has to be a rectangle. So the thing here is that you have to have a parallelogram first. Once you know that, and it has one right angle, then it's a rectangle. And then the next one is, if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle also. So again, you have to have a parallelogram first, and then if AC and BD are congruent, then you know it's a rectangle. And remember what comes along with that. If something's a rectangle, opposite sides are congruent, all of the angles are 90 degrees. So let's say a manufacturer builds a mold for a desktop so that AB is congruent to CD, so this side here is congruent to this side over here, and that BC is congruent to DA, this one and this one. And then they tell us that the measure of ABC is 90 degrees. Why must this be a rectangle? So the first bit of information, that ABC, or AB is congruent to CD, and BC is congruent to DA. Because those two are congruent, this tells me we have to have a parallelogram. And then the fact that the measure of ABC is 90 degrees, this completes that first condition right there. I have a parallelogram with one right angle, so then ABCD must be a rectangle. So we basically had to prove two things here. We first had to figure out, is it a parallelogram or not? And then once we've done that, then we can say that that one right angle makes it a rectangle. So now conditions for rhombuses. There's one more condition than there is for rectangles. So the first one says, if one pair of consecutive sides are congruent, then the parallelogram is a rhombus. So this and this of a parallelogram means that it's rhombus. If the diagonals are perpendicular, then the parallelogram is a rhombus. And then if one of the diagonals bisects a pair of opposite angles, so this right here, we know that we have a rhombus. So let's prove this. I'm going to tell you that you have a parallelogram here, and I'm going to tell you that JL bisects some things. We need to prove why that makes it a rhombus. So let's write our two-column proof with our statements and our reasons. Now let's put our givens down first. So we have that JKLM is a parallelogram. Remember, that means a lot of stuff. And then we also have that JL bisects angle KJM and angle KLM. So all of these are given. So now, what does all of this mean? Well, the whole bisect thing means that I have congruent angles. If JL cuts through KJM, this one right here, that means the angle 1 has to be congruent to angle 2. And if it bisects this one up here, that means angle 3 has to be congruent to angle 4. And that's by the definition of an angle bisector. And then we have a shared side here. So even though we're not talking about triangles, it makes two triangles. So I know that JL is always congruent to JL because of the reflexive property. So using that, I have these two triangles. I know triangle KLJ has to be congruent to triangle MJL because of angle side angle. Now, once I've proven these two triangles congruent, I can use CP/CTC to prove that anything is congruent. So let's prove that JK is congruent to JM. And the reason I would do this is because of this condition right here. If you have consecutive sides that are congruent, then you know the whole triangle is. I could go around, or the whole rhombus is. I could go around and make sure that all of these sides are congruent, but this is enough right here to say that JK is congruent to JM because of CP/CTC. And that tells us that this is a rhombus, so that's our final thing down here, because of, if you have a parallelogram with consecutive congruent sides, you have a rhombus. So let's do an example. Determine if the conclusion is valid. If not, tell what additional information we need to make it valid. So they tell us that EF is congruent to FG. So this one here and this one here. And they tell us that EG is perpendicular to FH. So this right here. And then they draw the conclusion that EFGH is a rhombus. So let's think back to what we know about rhombuses. If they tell us that we have two adjacent sides that are congruent, or that the diagonals are congruent, we know that it is a rhombus. But remember, the stipulation here is that we have to have a parallelogram first in order to tell us that. So if we go back here, they don't give us any information telling us that this is a parallelogram. So this is not valid because we don't know if EFGH is a parallelogram. We need to know that before we can use any of these conditions that we have listed here. So let's try another one. Determine if this conclusion is valid. If not, tell what additional information we need. So let's say that EB, so here to here, is congruent to BG. FB is congruent to BH. EG is congruent to FH, so the whole thing here, this is kind of hard to show, but this is congruent to this. And that triangle EBF, so this one here, let's color it in, and this triangle over here, EBH, so this one here. So we need to prove if EFGH is a square. So remember, in order to prove that something's a square, we need to prove that it's a rectangle and a rhombus. And before we can prove if something's a rectangle or a rhombus, we need to prove that it is a parallelogram. So we got a lot of things to prove here. So step one, let's see, is it a parallelogram? So remember, we had several conditions for parallelograms. The one that I'm going to use is that both pairs of opposite sides are congruent. So from these triangle congruence things that they tell us here, I know that if these two red triangles that I have shaded in are congruent, that means these bottom sides here are congruent. And then the triangles that are across from each other are congruent by side angle side. So that means that all of these sides are congruent here. So yes, we know it's a parallelogram because opposite sides are congruent. So the next thing we got to prove is it a rectangle? And remember, these are the things we're learning today. To prove if something's a rectangle, it needs to be a parallelogram, which we have. We have to have one right angle, or the diagonals have to be congruent. So we come back over here, and remember they told us that these blue lines that we drew here, which are the diagonals, are congruent. It was this one right here. So yes, we know it's a rectangle because the diagonals are congruent. And it was the EG is congruent to FH. EH. And then the last thing we got to prove is it a rhombus? And if it meets this condition, then it has to be a square. So if we go back to our rhombus conditions, if one pair of consecutive sides is congruent, or if the diagonals are perpendicular, we don't know anything about this, so we're not going to use that one. And then if the diagonals bisect each other, again, we don't know anything about that. But we do know that consecutive sides are congruent because all of these triangles are exactly the same. So yes, it's a rhombus because consecutive sides are congruent. And we can say like the EF is congruent to, let's do EH. And that's because those two triangles are congruent. So because it meets all of these qualifications, then yes, it is valid, it is a square. It's kind of a lot of work to determine if something's a square. So we're going to do something in the coordinate plane now. Use the diagonals to determine whether it is a rectangle, a rhombus, or a square, and then give all the names that apply. So when we're using the diagonals, we have to remember what the relationship is. In a rectangle, your diagonals are congruent. In a rhombus, your diagonals are perpendicular. And in a square, they have to be congruent and perpendicular. So we're going to graph this, check it, and see what we can find. So let's go over 1 and up 1, 2, 3, 4. And then over 2, up 6. And then over 1, 2, 3, 4, up 1, 2, 3. And then 1, 1. So here's the shape we have. And just glancing at it, I would say, yep, it kind of looks like a square, but we need to prove that. So we want to take our diagonals, and we need to find out if they're congruent and if they're perpendicular. So let's find out if they are perpendicular first. So I want to find the slope of QS. So in order to do that, I'm going to do rise over run. I'm going to go up 1, 2, 3, 4, 5 over 1. And then I got to find the slope of PR. So I'm going to go down 1 over 1, 2, 3, 4, 5. Down 1 over 5. And then to check to see if they are perpendicular, multiply them together. Does 5 over 1 times negative 1 over 5 give you negative 1? In this case, it does. So this means that they are perpendicular. So we have this. We know it has to be a rhombus. So now the next thing we want to prove is see if it could also be a rectangle. So what I'm going to do is I'm going to find the distance, the length of QS. And remember, you can use the Pythagorean theorem, or you could use the distance formula. It doesn't really matter. If you use the Pythagorean theorem, you're going to make a little triangle here and find the hypotenuse. So your a squared is 1 in this case. Your b squared is 5. We're going to find c squared. So I get 1 plus 25, get 26. So c is the square root of 26 long, 5 and some change. So let's find the length of PR, and let's do this one with the distance formula. So remember, you want to take your x's, find the distance between them and square it. Take your y's, find the distance between those and square it, and then take the square root. So let's use our points. The second x, remember we're doing p and r. The second x would be 4 minus a negative 1, and then add that to our y's, 3 minus 4 all squared. So you end up with 5 squared here, plus a negative 1 squared. If you look, you end up with the same thing, 25 plus 1, or the square root of 26. So that proves that we end up with two congruent diagonals here. So that means that this is a rectangle. And remember, if something is a rectangle and a rhombus, then it is a square. So we can name this 3 different ways. When it says give all the names that apply, it's a rhombus, a rectangle, and a square. So you should be able to prove that a given quadrilateral is a rectangle, a rhombus, or a square. And obviously it could be none of those. We're going to do plenty more problems like this in class tomorrow, so make sure you write down any questions you have and we can go over them then. Have a good night.